Hello, my name is Ephraim Fonzi Pardillo. I'm going to talk about differential leveling. Basic concept: differential leveling is the process of determining the difference in elevation between two or more points at some distance apart. Let's go to the important terms. Benchmark: a fixed point of reference whose elevation is either known or assumed. They may be permanent or temporary. Backsight: reading taken on a rod held on a point of known or assumed elevation. First rod reading taken after the instrument has been set up and leveled. Foresight: reading taken on a rod held on a point whose elevation is to be determined, usually taken in the direction in which the leveling work proceeds. Backsight or foresight distance: distance from the center of the instrument to the rod on which a backsight or foresight is taken. Turning point: an intervening point between two benchmarks upon which point foresight and backsight rod readings are taken to enable a leveling operation to continue from a new instrument position. Height of instrument: elevation of the line of sight of an instrument above or below a selected reference datum. To fully understand these terms, let us proceed to the process of differential leveling. Here we have two benchmarks, the known benchmark and the new benchmark, and we are going to calculate the new benchmark by proceeding from left to right. By reading the left rod on a known benchmark, it will become the backsight reading, because a backsight reading is a reading on a point of known elevation. And to get the HI, we simply add the known elevation plus backsight reading. Here we got 842.17 plus 4.69 equals 848.86. The next is we will pick a point to become our turning point, and there we will build our new rod or put our new rod, and the reading that will be taken there will be our Fs, since Fs is a reading on a point of unknown elevation. And to calculate for the unknown elevation, we simply subtract the height of instrument minus the Fs reading. So 848 minus 86 minus 6.08 equals 840.78. As you can see, this will be the elevation of our turning point 1. Next is, as we go from the left to right to calculate for the elevation of this new benchmark, we will repeat this process. We will move the instrument to the right and then read the reading to the turning point 1, and it will now become the BS, backsight reading, because at this point the turning point 1 has a known elevation. And just like then, we will add the elevation plus the backsight reading to get the height of instrument, and then repeat the process to get the unknown elevation of turning point 2. We will subtract the Fs from the HI, and then as you can see, this is the pattern that I've been trying to explain. We just simply need to add the elevation plus BS to get the HI, and then subtract HI to Fs to get the new elevation, and repeat this process until we solve the new elevation of the benchmark or the final elevation. After doing so, we will compare the known elevation and the calculated elevation. As you can see, it is different, 842.17 and 844.96. Checking of measurements. To know whether our measurements are true and correct, we will need to conduct two ways of solving the elevation. One is in forward way, which we did earlier, and one is in reverse way. In forward way, we did it by left to right, and in reverse way, we will do it from right to left. As you can see here, there are new values below the elevations. One is inside a parenthesis and one is outside the parenthesis. The one inside the parenthesis are the values of elevation that were solved using forward way, meaning those are the previous value elevations. When we finish solving the final elevation using reverse way, we will then compare the elevation difference between the two. So in forward way, we have an elevation difference of 2.79 feet. This is calculated by subtracting the final elevation, which is 844.96, minus the known elevation given, which is 842.17. In reverse way, the elevation difference is negative 2.81 feet. This is calculated by the final elevation, which is 842.15, minus the starting elevation, which is 844.96. Note that the larger the difference between the two elevation difference, the more it is unacceptable. So to know whether our difference is large or not, we are going to subtract these two values, which is 2.79 feet minus 2.81 feet, which is negative 0.02, which is small enough to be acceptable. To further see whether our calculations are correct, we should perform closure error. This is done by subtracting calculated elevation to known elevation, which is the 842.15 minus 842.17 equals negative 0.02 feet, which is the same as the one we did earlier. That means our measurement and calculations are almost perfect or perfect. Next is differential level notes. To do differential level notes, we need to create a table of 5 columns. Each column is labeled as station, backside, height of instrument, FS, and elevation. Elevation here is already given in the problem since it is already there. And then since we record first the backside, it's only natural for us to input the backside value first on the benchmark row. And then when we calculated for the HI, we added elevation and BS. So we will just do it on the table the same as how we did it on the illustration. The next is we solve for the FS from the TP1. From the TP1 row, we solve the FS and elevation by subtracting the HI minus FS, which is the new elevation of TP1. And always remember this kind of pattern where we add elevation and BS and then subtract HI minus FS, because we will going to repeat that until we get to the bottom. So as you can see here, when we record the note of BS, we then added them together to get the new height of instrument. And then for the TP2 elevation, we subtracted the HI to the value of FS and then repeat the process until we reach to the bottom. Now we are done, but this is the forward way only. Remember that we did the forward way and the reverse way, and now let's do the reverse way. In doing the reverse way, we will continue to where we end. Since we ended here in the new row, we will start here. So 844.96 will be added to the BS, and then subtract the HI to FS, which will be our new elevation, and then continue here. This is just the same elevation is 842.66 and 842.66. Notice that there is already an inputted value here on the BS column and the FS column. That's because this is another way of taking notes for the differential leveling. This is done by recording the values of BS first, and then FS, and then BS, and then FS, and then so on and so forth. After you tally all their values, that's the time you are going to calculate everything once and for all. So by doing the repeated pattern again, which is elevation plus BS, and then HI minus FS, we will get the value of HI and the elevations. As you can see here, it is done. And then we have two values of elevation. One is in the black color and one is in the red color. Those in the red color that are inside in parentheses, those are values of the previous elevation. See here that TP4 has a previous elevation of 842.67. TP3 has a previous elevation of 836.17, which can also be seen here from the left table. 836.17 for TP3, 842.67 for TP4. After doing all the recordings for the notes or tallying, we will then do an arithmetic check to further assure whether our calculations or recordings are all true and correct. To do the arithmetic check, we will simply add all the BS values and the FS values. Previously, from here, the BS value starts from 4.69 and end from the 7.80. So from there to here, we will add them and get their sum. Same as to the FS values from 6.08 to 6.41, the sum will be their value here. After that, we will going to follow this formula, which is the starting elevation plus BS sum minus FS sum equals measured ending elevation. Note the starting elevation here is the first elevation that you will see on the table, and the measured ending elevation is the last elevation you will see on the table, which is 842.15. So meaning that we will need to expect a value of 842.15 for us to know that our measurements and calculations are correct. So let's see. 842.17 plus 56.99, which is our BS sum, minus 57.01, which is our FS sum, equals 842.15, which is exactly the same as our last elevation value, meaning that we have a good and perfect calculations from our table. Sample problem. On this problem, let us try to solve and fill up all the necessary values on this table. So remember that there is a pattern on filling up this table. Elevation plus BS equals the HI, and then HI minus FS equals the new elevation. So let's go and try to apply that. 127 minus 133 plus 1.256 equals 128.389. 128.389 minus 1.886 equals 126.503. 126.503 plus 1.116 equals 127.6109 minus 1.527 equals 126.092 plus 1.228 equals 127.32 minus 2.246 equals 125.074 plus 1.189 equals 126.263 minus again 2.017 equals 124.246 plus 1.07 equals 125.316 minus 2.656 equals 122.66 plus 1.831 equals 124.491. Finally, for the final elevation, 124.491 minus Fs, which is 2.765, equals 121.726. Now, after filling up all the values here, we are going to solve for the total sum of the Bs values and the total for the Fs values. For the Bs values, we have 7.69. For the Fs values, we have 13.097. After doing that, we will do the arithmetic check. Here, I am simply substituting the values, which is elevation BM1 or starting elevation, which can be seen here as the first elevation on the table, 127.133, plus the total Bs values minus the total Fs values. As you can see, our answer here is equal to the final elevation value on the table, 121.726. That means that we did our calculations correct. That's all.
Hi everyone, my name is Charles Limbaga. I'm here to discuss about profile leveling. So, profile leveling is the process of determining the difference in elevation along a fixed line at designated short measured intervals. It is executed to provide data from which a vertical section of the ground surface can be plotted. The main difference between the differential leveling and profile leveling is the number of foresights taken from each setup of the instrument. To further understand what is profile leveling, I will show you a video that discusses more about profile leveling.
In the last video, you saw the field process and note keeping for a benchmark leveling circuit. Also called a differential leveling circuit, this survey used multiple instrument setups, and at each setup, the surveyor measured one backsite and one foresight. In keeping with the adage, measure twice, cut once, the level circuit had a forward run and a reverse run. Because this level circuit ended where it began, we call it a closed loop circuit. Since there was only one known benchmark available, all the elevations in the survey are measured relative to that one benchmark. Let's suppose two known benchmarks are available near your project site. You plan to create a new benchmark, but which known benchmark should you use for your survey? Benchmark A or benchmark B? If benchmarks A and B were created in the same original survey, then you can use both. Start the level circuit on A and end the circuit on B. We call this a closed link circuit. That is, your new level circuit links between two known benchmarks. Link and loop level circuits both begin and end on known benchmarks. Ending on a known benchmark makes the level circuit closed. At the closing benchmark, you can compute the closure error in the circuit. If there are closed circuits, then it's possible to have an open circuit. In surveying, an open level circuit does not end on a known benchmark, so it contains no check for blunders and errors. For instance, if we skipped the reverse run of the closed loop circuit from before, it would instead become an open circuit. Because an open level circuit does not self-check like a closed circuit, you should always use closed level circuits.
So far in this video series, we've explored benchmark leveling. It's a great place to begin learning, but there is a more common leveling method we use to solve all kinds of problems.
Imagine that your farm has a grass waterway like this one. When properly constructed, this waterway reduces erosion, prevents ponding, and allows easy travel by vehicles and machinery. The waterway profile, that is, the changing slope along its path, must harmonize these goals. However, your waterway has a ponding problem. So how do we begin to solve this problem? We can use a method called profile leveling. The idea is to measure the elevation at intervals along the waterway profile. Equipped with this information, we can design a new waterway profile and excavate the soil that caused the ponding problem. Here's a simplified map of your waterway. Computing waterway slope requires not only elevation difference, but also horizontal distance. For simplicity, we use a system called stationing to indicate horizontal distance. Very similar to mile markers along a highway, stations tell us the distance from an origin point. We'll mark the low end of the waterway with a wood stake labeled with station 0 plus 0, 0. The plus sign in this station is a placeholder between the tens and 100s places. The plus sign identifies this number as a location, just like the highway mile marker. By measuring along the waterway center line, we can mark a new station every 100 feet. Remember, the plus sign in this station is a placeholder between the tens and 100s places. So when we've measured 100 feet from the 0 plus 0, 0 origin, we can mark that as station 1 plus 0, 0. Station 2 plus 0, 0 is 200 feet from the origin. Station 3 plus 0, 0 is 300 feet from the origin. This system allows more specific locations as well. The deepest ponding in your waterway occurs at station 6 plus 72. Station 6 plus 72 is 672 feet from the 0 plus 0, 0 origin. Now that we have the stations marked, it's time to use profile leveling to measure the elevation at those stations in the waterway. We'll set up our instrument where we can see the starting benchmark and several of the station marks. Our first rod reading is a backside on the benchmark, and our first foresight will be at station 0 plus 0, 0. Instead of moving the instrument like in benchmark leveling, we can continue reading the rod at the next station marks. When distance or obstacles prevent us from taking more readings, then we'll establish a turning point and measure a foresight there. Remember that in benchmark leveling, for every instrument setup, there is one backsight reading and one foresight reading. However, in profile leveling, for every instrument setup, there is still only one backsight reading, but there can be several foresight readings, as you see here. This is the primary difference between benchmark leveling and profile leveling. After reading the foresight at the turning point, we'll move the instrument where we can see the turning point and the remaining station marks. With a backsight reading taken at the turning point, we're ready to read foresights on the waterway stations. There is another benchmark nearby, so we'll close our level circuit there with a final foresight reading. Since we didn't return to the starting benchmark, this is now a closed link circuit. That's how the process will look. Let's wade deeper into the water and explore proper note keeping and computations for profile leveling.
So how do we compute in profile leveling? The first step is to know the elevation value of each benchmark. Knowing the elevation values of each benchmark is a common practice as civil engineers. So we have the elevation value, which is 585.95, and we measured already the backsight value. In order to get the reading for the height of instrument, we only have to add the elevation value with the value of the backsight value of benchmark A, which is 9.33. So 585.95 plus 9.33 is equals to 595.28. This is our value for the HI of benchmark A. Notice that we don't have any values for the foresight in benchmark A. It is because the first foresight value is recorded in the station 0 plus 0, 0. This is our first foresight value. Now, to get the elevation value for station 0 plus 0, 0, we have to use this value, the height of instrument from benchmark A, and subtract it with 6.60, the value of the foresight of station 0 plus 0, 0. So subtracting them together will result to 588.68. Notice that we don't have any backside values. It is because we only have one backside value because we didn't move the instrument from here to here and so on. So the instrument is only stationary. We only move its length in order to get the values. So we have to use this value again in order to get the elevation value of station 1 plus 0, 0. So 595.28 minus 5.76. The result would be 589.52, the elevation value for this. The same process same steps will be followed for these values. Like we get the elevation. How do we get the elevation value for station 2 plus 0, 0? Same process, 595.28 minus 4.55 is equals to 590.73. Now we want to know the elevation of station 3 plus 0, 0. You have to use this value again and subtract it with the values here, and the result will be here. So same process ra gyapon siya. Same process, we use this value to use this value and subtract it with these values in order to get the elevation values of each station. Notice that we have a turning point here. It is because we're not able to determine the foresight value, or it's not too clear. That is why we took a turning point and measured its foresight value, which is 1.66. Here we took a turning point and placed our instrument here. Then we measured its backside value, which is 7.62, and the elevation value of this turning point is 593.62. It is we got this from here. So since we have a new backside reading, we have to get the new value for the height of instruments in order to get the elevations of each stations here. So 593.62 plus 7.62 would result to 601.24. Now we are curious to know the elevation of station 6 plus 0, 0. We have to use this value again, 601.24, and subtract it with 10.04. And this would be the answer, or this would be the elevation value. Same process for this. Same process ra gyapon para dire in the pita. Same process. Subtracting 601.24 with 10.06, the result would be 591.18. Subtracting 600.24 with 9.55, the result would be this. And same process rin ni sila gyapon. This value is the elevation value for benchmark B. As I mentioned earlier, we have to know, or it is important to know, the elevation of each benchmarks that we use in surveying. So to do the arithmetic check, first is to get the total backside values. So adding these two together would result to 16.95. Now, second, we have to get the foresight value. We only need to get the values that we are only interested or to these values. This because these values here are the things we measured, or we only measure this from here bitaw. We only these values. We only need to use the values that we made a turning point and the benchmark value that we ended. That is why we use these two. If there is a turning point 2 here, for example, we have to add the values together, and so there's three things na para tong i-add to get the total, and three things for the foresight value na sad. So to continue, or like for better understanding, to get the backside value, we have to get the total backside value that we made from the benchmarks and turning points. And for the foresight, and to get the total foresight, we are only interested to the values of the turning points and the benchmarks. So to do the arithmetic check, the starting elevation plus the backside sum and minus the foresight sum. Foresight sum is, and we will get the measured ending elevation. For example, 585.95 is our starting elevation. Then we added it with the backside sum, which is 16.95. Then we subtract it with 5.23, which is the foresight sum. The answer would be 597.67. So these values match. So there is no discrepancy of these values. For better understanding, here are the formulas to remember. Here's a sample problem. Complete the following set of profile level notes above and perform the customary arithmetic check and plot the profile. So feel free to pause the video for you to solve for this profile level notes. So let's proceed. So here's the answers for the problem. So to get so here's the process. First is to know the elevation value. So the elevation value is given already. So it is 125.5, and we had a backside value which is 0.95. To get the height of instrument for the benchmark in the benchmark A, we have to add the value of the elevation and the backside value of benchmark A to get the height of the instrument. So adding them together will result to 126.45. So to get the elevation value for the station 0 plus 0, 0, we use this value 126.45. Since there's no new bauxite reading, we have to use this value again. So 126.45 minus 3.0, the answer would be 123.45. So for the next station, station plus 10, since there's no new bauxite reading, we have to use this value again. So 126.45 minus 2.3, we will get this value, 124.15. Again, to get the elevation value for station plus 10, since there's no new reading, we have to use the value of the height of instrument in the benchmark A and subtract it with the value with the intermediate foresight, which is 2.3. So the result would be 124.15. Since we cannot, or we're not able to determine the, the foresight values, we made a turning point in order to see to acquire the values, the foresight values for these stations. So to get the elevation for turning point 1, we have to use this value 126.45, and since since we have the foresight value prior to moving, we have to uh, measure the value or record the value before before uh, moving our equipment or instrument. So this is the value for the foresight reading in the turning point 1. So 126.45 subtracted by 0.64, the answer would be 125.81. Since we have a new bauxite reading, we have to compute for the new reading for the height of instrument. So we have to add the elevation value of the turning point 1 to the value of the new bauxite reading for the turning point 1. So adding these two data together, the result would be 128.94. So we have a new height of instrument because since we have a new value of height of instruments because we have a new bauxite reading, so we have to use the new value or reading that we acquired in order to get the elevation value for these stations. So since we have a new bauxite reading, we have to use this, not this. So 128.94 minus 2.7, we will get the elevation value of station 0.22, which is 1. The value would be 126.24. Now to get the elevation value of station plus 30.5, same process as we did here. Use this value and subtract this value with the value 2.8 in order to get the elevation value. So same process as we go down. Then since we took another turning point, so we use this value 128.94 minus 1.28. The answer would be 127.66. Since we took a turning point, there will be always a bauxite reading. So we have to compute for the new reading for the height of instrument. So we have to add the value of the elevation value of turning point 2 and add these two together. 127.66, the elevation value for turning point 2, plus that bauxite reading, or the new bauxite reading, which is 2.16, the answer would be 129.82. Since we took another, or since we have a new box or new reading for the height of instrument, we have to use this value in order to get the value for this new, or for the values for the elevation. So in order to get the elevation value for station plus 45, we have to use the new reading of HI and subtract it by 0.9, which is the result would be 128.92. And then to get the elevation value for this station, same process as we did here. New HI minus the foresight value, the station, we will obtain this new elevation value. Same process, same process for this data, since there's no new bauxite reading, or we didn't made another turning point. So same process ra gyapon. And then we took another turning point, since we're not able to determine the values here, the foresight value. So we took another turning point. So in order to get the elevation value for turning point 3, we use this value, 129.82, and subtract it by 2.37. The answer would be 127.45. Since there's a new bauxite reading, the elevation value plus the new bauxite reading, 0.82, we will get the new reading for the height of instrument, which is 128.27. Now, we were not able to determine the foresight value. We made another turning point. So using this value, the height of instrument, in order to get the elevation value for turning point 4, we have to use the value for the reading of HI in turning point 3 and subtract it by 3.5, the foresight value of turning point 4. So the result would be 124.77. This is the elevation value for turning point 4. And then, since there's a new bauxite reading, or we made a new bauxite reading, we have to add these two together, elevation value plus the value of the bauxite. We have to, we are now, we obtained the new reading for the HI for turning point 4, which will be used in getting the elevation for station plus 75. So in order to get the station plus 75 na elevation value, since nanatay since we were able to determine a jud sa foresight value, we use this value and subtract it by this value. So subtracting the HI value by the foresight value, and this would be the result. So we have the elevation value for this station, and then we made the foresight value for the benchmark B, since it's a close link type. So we measured its foresight value, which is 1.99. So we still use this value, 126.12 minus 1.99. We will get 124.13, which is the elevation value for benchmark B. And this is our data, the table or the profile level notes. Now to get or to do the arithmetic check is to first is we have to get the summation of the values of the bench backside values that we use, which we are only interested with the benchmarks and the turning point values since we didn't move the instrument station by station. So so there's only 1, 2, 3, 4, 5 values that we need to add to get the total or the summation of the backside value. So we added them together. The result would be 8.41. Now to get the summation of the foresight, we have to add these values since we are only interested with the benchmark values and the turning point values. We so we on, so we only add this 1, 2, 3, 4, 5 these 5 values together in order to get the total foresight. Notice that I made a new column. It is because to avoid confusion, because if you put it here, there's a tendency that you might use 2.3 instead of 0.64 as the value that we needed to add in order to get the total foresight. So that is why we made a new column. This is the foresight value and the intermediate foresight values. The only difference is these are the stations and the foresight values are the data here are all in the turning point and benchmark, and the data here are all are from stations. So we added these values and we're able to get 9.78. Now to get the or to do the arithmetic check, we have to add we have to add the starting elevation with the total backside value, which is 8.41. So 125.5 is equal plus 8.41 equals to 133.91 minus 9.78. So the value for our arithmetic check is 124.13. So our values match with this. So there's no discrepancy in our notes. So to plot the points, we we are only interested in the stations and elevations. So there's no need to put the data for the turning point and benchmark. Instead we only inputted the values for the stations, the 0 plus 0 0 plus 10, 0 plus 22 from this is the one station. There's no turning point or benchmark here, and these are the elevations value. That would be all for profile leveling.
Report about reciprocal level. So, good morning, everyone. I am Elijah Joseph Lisen, and I'm here to report about reciprocal leveling. So, what is reciprocal leveling? Reciprocal leveling is a surveying method between 2 points at great distances, where height measurements are taken at both directions to eliminate possible atmospheric and curvature errors. So in the case of a river or valley, it is not possible to set up the level midway between the 2 points on opposite banks. In such case, the method of reciprocal leveling is adopted, which involves reciprocal observation of both banks of the river or valley. So, in reciprocal leveling, the level is set up on both banks of the river or valley, and two sets of staffs staff readings are taken by holding the staff on both banks. In this case, it is found that the errors are eliminated and true difference of level is equal to the mean of the true apparent differences of level. So, what are the procedures in doing reciprocal leveling? And the first procedure is, suppose A and B are 2 points on an opposite bank of a river. The level is set up very near A, and after proper temporary adjustment, staff reading are taken at A and B, and their readings are A1 and B1. Then the next step is the level is then shifted. So you transfer the staff and put it at the other side. So it is set up very near B, and after proper adjustment, staff reading is taken as A and B. So suppose the readings are A2 and B2. And after taking both of the staff readings, we then move on to the true difference equation, which is dE1 plus dE2 over 2, which is simply A1 minus B1 plus A2 minus B2 over 2. So you just simply put in the values of A1 and B1 here, and A2 and B2 here, and you divide it by 2. So our next slide is a video showing deeper understanding of reciprocal leveling and a sample problem which you can solve.
Hello everyone, welcome to Tips and Tricks. In this video, we're going to see about reciprocal leveling. And before we start, I would really appreciate it if you could smash that like button, drop me a comment, and share this free program with anyone who might need it. We have already seen the error due to curvature. I have the link to it in the description box below. In this video, we are going to see how we can eradicate it. We can see that we have a river here. I already know the reduced level at A. I need to find the reduced level at B. Since this is a river, I can't place my leveling stuff here. If I can place it here, the distance will be less, and therefore my error due to curvature will also be less. Since this is a river, I have to place it only in the bank. Since the distance is increased, my error due to curvature becomes prominent. This can be eradicated using reciprocal leveling. Reciprocal leveling is where we take readings of 2 points from 2 different stations. So my points are A and B. I have already set up my leveling stuffs there. First, what I'm going to do is I'm going to set up my auto level or dumpy level, my leveling instrument, very near to the station which I already know. I already know the RL of A. I'm setting up my level very close to it. From here, I'm going to take readings of station A and B. So when I place it very near to A, there will be no curvature error here since the distance is very less. So the answer which I'm going to get here, that is the reading which I get from the leveling staff, is going to be my true reading. There will be no error due to curvature. Whereas when I'm taking the reading here, the distance is increased. Because of that, there will occur a curvature error. You can see that this is my horizontal line. This dotted line is my line of sight. Line of sight is what we see from the telescope of our level. And this is my level line. We already know that the reading corresponding to our level line is only our true reading. But our line of sight, it gives some other reading. But due to the curvature error, our level line will be below it. So in order to find the true reading, I have to subtract these two. HB is the reading which I have got from the line of sight. From HB is the value which I see through the telescope. But my level line lies here due to curvature error. So my true reading is going to be HB minus the curvature error. Similarly, we are going to set up this station, the leveling instrument, very close to B in the next set of readings. Since I am placing the instrument very close to B, the reading which I am going to get from this staff is going to be free from any curvature error. Whereas when I take the reading in this staff, there will occur a curvature error, and therefore my true reading will be similar to this case. It will be something like HA dash minus E. And another thing you have to note here is this is HA, HB, HB dash, HA dash. The readings taken from the station close to the point which we don't know the RL. We don't know the RL of B, right? The readings taken with the station placed near that point has dash values in it. So I have to find the level difference between these 2 points. From that I can find the RL of this. In order to find the level difference, we have to simply subtract the staff readings. So my staff reading and for the first case is HA minus my true reading. So it is HA minus HB minus E, which gives me HA minus HB plus E. For this case, it is HA dash minus E minus of HB dash, which will be HA dash minus HB dash minus E. This is equal to the level difference. Say it is H. So we have something like H is equal to this, H is equal to this. But we only know the values of HA, HB, HA dash and HB dash. We don't know the values of E. So in order to eliminate these two things, this is plus, minus. In order to eliminate these two things, we are going to add our case 1 and 2. Solution, our equations 1 and 2. So this will give us H plus H is 2H is equal to, on simplifying these things, these two will get cancelled, plus and minus will cancel. On simplifying we will get HA minus HB plus HA dash minus HB dash. This can be even more simplified as H is equal to half into HA minus HB plus HA dash minus HB dash. So now I need to find the value of B. I need to find the RL of B. First we have to substitute all the values and get H. Now if my H is positive, then my RL of B, that is the RL of the station which I don't know. This is a small trick here to save time for you. If my H is positive, then the RL of B is going to be my RL of A plus H. If H is negative, then RL of B is equal to RL of A minus H. This will save you lots of time in the exam, else you have to use the logic and find the RL. This will help you even more. So now if they ever asked the error due to collimation, then you can simply modifying this formula will give you the answer. It is H is equal to the same 1 by 2 into HA minus HB, but here it is minus HA dash minus HB dash. Now to understand this better, let us look into a problem. This problem was asked in GATE 2007. The problem goes like this. The following measurements were made during testing of a leveling instrument. Instrument at P and Q, staff reading at P dash Q dash. The values are given. P1 is close to P, Q1 is close to Q. If the reduced level of station P is 100 meters, the reduced level of station Q is how much? They are giving you options. This is a 2-mark question. It is, as you can see, it is simply formula substitution. We know the RL of P, so the staff reading notations will be A, B. We don't know the value of Q, so it is A dash, B dash. On substituting it in our formula, H is equal to 1 by 2 into HA dash minus HA minus HB plus HA dash minus HB dash. This 1 by 2 into HA minus HB is 2.8 minus 1.7, which is 1.1, plus HA dash minus HB dash 2.7 minus 1.8, which is 0.9. So this is 1 by 2 into 2. So the difference H is 1. So since it is positive, my RL of unknown, that is the RL of B, is going to be, I know the RL of 8 is 100. See, RL of B is going to be 100 plus, since it's positive, plus 1, which is equal to 101. It's equal to 101 meters. This is our answer, option C. If you like this video, please do give a thumbs up and subscribe to the channel. It will really motivate me. See you guys in the next video. Bye.
Hello, my name is Israel Abram D. Velasco, and I'm going to discuss about double-rotted leveling. So, double-rotted leveling is a form of differential leveling in which a continuous check is maintained on the accuracy of the leveling procedure. So, it is useful when there is an urgent need to undertake differential leveling in a short period of time, where no established benchmarks are available for checking results. So they provide a continuous check on the process of determining ground elevations while the work is in progress. So double rodding can be done most conveniently by two rodmen. So for the procedure of double rodding, so first you determine the height of the instrument at each setup point by backlights then taken on two different turning points. So if no mistake or large error has been made, the result will be two height of instruments that will differ slightly from each other. So elevations computed this way will also differ slightly, and in each case, the average is taken as the evaluation. So here is an example of a double-rodded leveling. So a higher TP and a lower TP was used, which results in two different heights of instruments for each. So computed by the higher height of instruments, the elevation of benchmark 2 came to 851.98 feet. Then for the lower height of instrument, the benchmark 2 came to 852 feet. And since the mean is used for their elevation, it resulted to 851.99 feet. So next is the video for further understanding of the topic.
Okay, so let us now proceed with double-rodded leveling. Now, the difference between double-rodded leveling and differential leveling is the name itself, double-rodded. So we have two rods. Okay, so the concept is still the same. The computations are still the same. The only difference is that we have another rod to take into account. Okay, so the advantage of using double-rodded leveling is that when we get to BM2, we have two values for BM2, right? And then we can take the average of that to get a more precise result compared to differential leveling. Okay, so let's examine our setup here. So we have here BM1 with an elevation of 205.549. And then the yellow setups here. So by the way, this is a top view. The yellow setups here with a crosshair are our instrument setups. And then TP1H and TP1L. So the H and the L are just used to differentiate between the two rods. Okay, and then we have TP2H, TP2L, and TP3H, TP3L. The green observations are the back sights, and the red observations are the fore sights. And then lastly, we have our BM2 here, which elevation we do not know yet. Okay, so let's examine the table, tabulated the values. Okay, so as you can see, we have here the elevation of our BM1. So we duplicated this because just to be consistent with the other values, because we have two values for the TPs. So just for consistency. And then you add the backside to that. So from your first setup, you take a backside at BM1, right? And then you add that to the elevation of BM1. Then you will get this height of instrument, which is the same. Okay. Okay, now from this setup, if you want to get the elevation of TP1H and TP1L, we take the foresight to those two rods. We have here 1.104 and 1.549, right? Then if you want to get the elevation of TP1H and L, then you subtract the height of instrument, the foresights from the height of instrument, 207.513. So you will get these two values right here. Okay, so and then you transfer your setup, and then you take a backside at TP1H and TP1L. So here they are 2.187, 2.629. Then after that, if you want to get the new height of instrument, you add the elevation of TP1 to those backsides. Okay, so you will have these two values right here. So we now differ because our TPs have different locations. Okay, so basically do that over and over until you get to the elevation of BM2. As you can see here, we have two different values. Now we will take the average. Now the average is, so that will be 202.887 plus 202.863 divided by 2. So the average value is equal to 202.875. Okay, so now it's time to do an arithmetic check, right? So to do an arithmetic check, we sum up the backsides. So if we do that, we will get a positive 12.975. And we sum up the foresights. So that was the backsides, and this is the foresights now. Then we will get negative 18.323. It's negative because we subtract the foresights, right? So we just added all of these right here. So we will take the average later. Okay. So let's add up summation of backside. Summation of backside plus the summation of foresight. So we will get negative 5.348. Okay. And now we get the average of that. The average of that one will be negative 2.674. So you basically just divide this by 2 and you will get this. Okay. So now that we have this average, let's take the elevation of our BM1. Elevation of BM1 plus this average. Now if this will equal to 202.875, then it means that you've done the arithmetic correctly. Okay. Okay, so that's basically it for a double rotted leveling. So I hope you've refreshed your memory or learned something new in this video. And I will see you in the next video for 3-wire leveling. Okay, thank you for watching.